Put yourself into the situation in Pythagorean era that the people did not accept irrational number. So all that you can understand is rational number. But you can keep squaring numbers such as 1.4, 1.4.1. Those are a rational number we understand. But if you square that, it becomes closer and closer to the 2. Becoming, closer to 2. But you know there's no number. If you square it, becomes exactly 2. They couldn't find it and realized it never happens. Yes, but they didn't know. And for a long time, they didn't believe it. Is that a number? I don't understand. Nobody can visualize it. So there's that thing, the limit behavior. It is going there, but there's no solution that actually hits that. This type of thing happens a lot in mathematics. And to complete it, we call completion, or geometrically, it's called compactification. The world we have it here is closer to that solution, but not really the solution, such as the Taylor series. Taylor series is never ending, right? Something like that. So that's a completion idea. So something like that is about to happen. And at the beginning, gave a lot of trouble to some people. So here is an important function. I'm going to call it delta H. Delta H starts at 0. And there is a little spike in there. And then comes back down. That's what this delta H is. And here's a 0, and here's H. And the height is 1 over H. And H is supposed to be a small number. So it corresponds to a pulse in the force. Like beeping pulse like that you see in the hospital. So that, and if you shift it, this will switch to exactly the same fashion, but it starts at C. So here's a C here and C plus H. And the height is 1 over H. So this models the pulse function. Cool? And this function has interesting property, and that's why they focus on that. So you stick in that function into the integral, and you can multiply by function, like Laplace transform. There's that function, and you multiply it. Because this guy's a 0 here, this delta is going to kill everything about ft, right? Only gives you slight window of c to ch, c plus h. Everything else is going to be multiplied by 0, right? That's the only thing you're left. Here's ft. And this value here is 1 over h dt. That's what's left before you take the limit. But h is not, it's a fixed constant. For the integral, you can pull out f of t dt. This is known as a fundamental theorem of calculus part 1. Many of you remember fundamental theorem calculus only part 2. Integrate it and subtract b minus a. That's part 2. More theoretical version of fundamental theorem says the following. If you start with a c and c plus h, you integrate and divide by 1 over h, then it's just simply derivative of this whole thing. If you think about it, this is derivative, and this is f of c. Okay? So here's the thing. If h is becoming smaller and smaller, being positive, what happens to this function is that narrower and narrower, and it's getting taller and taller. 1 over h going to infinity, right? Over here. So if you push this h all the way to the 0, this is a nonsense. This point goes shoot to infinity, and there's nothing in between. So the limit h approach 0, the delta itself is a nonsense. But if you put that in the integral, and it makes sense. It gives out a certain sensible number. So this is what we are actually thinking, but they're lazy and decided to drop all that h thing and decided to just use this notation. So what is this delta, plain delta t minus c? It's not a number. It's just a shorthand notation of this phenomenon in there. We do that a lot when you're using dx and dy separately, Leibniz's notation, or when you're using the Riemann sum and the dx and dy. In the beginning, Leibniz invented the notation. Everybody loved it, But if somebody asks, what is dx? Do you mean delta x? That delta x in there? That's what people think. But delta x, the dx is not delta x. So it waited a long time, and mathematicians gave a solid foundation we call the differential form. I also introduced it in Calc 3. But this one still does not have a name. But it was invented by fearless physicist Paul Dirac, and he decided to call this one as a function, and other people call it a Dirac Delta function. But it is not a function. So we better name this a Dirac Delta non-function. It's not a function, right? But it is a shorthand notation of this phenomena. So they decided to drop this notation right like this, as if we are multiplying this ghostly Dirac Delta function and ft and integrate. That's not what it is. So if you actually multiply there, if c is in between a and b, it picks it up. If c is outside a and b, they're all 0, so it is 0. So it does something like that. But there is no such function, Dirac Delta function. It's not a function. It's just a notation to capture this phenomenon. Kind of makes sense? So here's another better way of looking at here. We're going to apply this one to Laplace transform. So they define the following. If you're multiplying Dirac Delta non-function into ft, and then what that means is that you actually play with the actual Dirac h function. Okay, this is actually function. I defined it to you with h in it. You multiply it and calculate it, and then send h to the 0 from the right, and then this whole thing makes sense. And they decided to abbreviate that with this one as if delta is a function. But what this one here is, by definition, is this. Again, this delta is not a function. You replace it with a delta h, you calculate it, and send h approaches 0. And whatever you get out of there is this meaning of this notation. So I'm going to calculate this one. Laplace transform of a 0 to infinity, e to the negative sh, this delta h, right? T minus c dt. By definition, we're going to calculate this with h. We're sending this one to infinity, sending h to 0. So this makes sense. This is actual function with h in it. But this is only supported between c and c plus h. Remember? Yeah, it's the only thing that survives there is a c and c plus h. So all this thing dies is only about c and c plus h. There's 1 over h again, e to the negative st dt. So h goes outside. I said this is a fundamental theorem of calculus. All you have to do is to plug in c into this function there, where t is. So this one approaches e to the negative sc. Have you seen e to the negative st? We've seen it a lot last time, right? So all the heaviside unit delta function. So, like that. So there is no actual function. The delta is not a function, right? There's no actual function. If you do the Laplace transform, you get e to the negative sc. Just like the square root. We can get to that really, really close using the actual function in here, right? Get really, really close. But you will never get that e to the negative sc using a function. Is the existence of that square root 2 to the Pythagorean people. But now we accept the root 2 as a function. Mathematicians still do not accept this as a function. It's not a function, something else, right? But still don't have a name. And everybody call this one what? Dirac Delta function. But it's not a function. So this is another important point of view to make here. So you will see an equation like this. Left-hand side is autonomous mechanical system, y double prime and y. And right-hand side is representing pulse. But this delta itself is not a function, right? So to make sense out of it, this is a real differential equation. There is delta H as a function. It depends on H, so this differential equation must have H attached everywhere. And you can solve this one using Laplace transform with initial value all 0, and it gets particularly simple, so you will see that. So the solution, we have H very small. We're going to send H equal to 0. And there, don't bother with this H thing. Just write it like this and calculate it as if delta is a function. Okay? So goes like this. If you apply Laplace transform to the left side, this initial value problem says s squared plus l1 y of s. This equation. Remember when you're applying the Laplace transform to differential equation, there's f0 and f prime of 0, but they're all 0, right? So it becomes simple, and represent this one as an algebra exactly like that. You'll see this example again. Right-hand side is a 3 times Laplace transform of Dirac Delta non-function, I call. Yeah? Anybody remember the answer to this one? What is Dirac Delta non-function? T minus 2. E to the negative 2s, right? Cool. So what is ys? 3 times e to the negative 2s, s squared plus 1, right? So what is y? Laplace inverse transform, right? Let's do the inverse transform. 3. What's the inverse transform here? Heaviside unit step function, right? And then we do the Laplace transform of this guy. Then shift it at the end. Isn't that right? That's right. So who knows Laplace transform of this one? Yeah, sine of t. But now you got to shift it, right? So is it t minus 2? Is that okay? That's a solution to this equation. But that equation is really not an equation. This delta is not a function, right? So the second one is what reality is. But that solution in here is going to be very, very similar to that one. So this solution here looks like this. Sine of t minus 2, sine goes like this. This is where pi over 2 is. Somewhere here is a 2. Up to here, it kills everything. It's all 0 here, right? After the 2, it picks up the sine. So function goes like this. But in reality, if you take the earlier function in here, where h is very small, if you graph it, you're going to do, you know what I mean? This one in here is not vertical, it's just actual, there is a time that it jumps. That one here is represented by this one. So rather than being like this actually, that ignore that, just deal with this ghost delta function, and you will get a pretty good answer. As you can see, this jump here creates a very high value of a derivative. High derivative. Don't you think? The slope is amazing. And if you do even second derivative, is it even higher? Therefore, it kind of makes sense that this double derivative is going to have a large and large value. But this one is a limit. You know, delta function has height 1 over h. As you push h 0 and 0, it's just going to be really high, which is going to be picked up by its y double prime in this actual version of the function. So they ignore this actual h in there. Just deal with it, and you get this one, and that'll be good enough. And you know it actually connects in reality with a big jump here, right? So that's a pulse added in there. So that's left-hand side is autonomous system, right-hand side is an external force added in there. But this external force is pulse. And you're not going to see in this example in here, this delta, Dirac delta non-function is multiplied to anything. It is added to the source. So this is all you need to know. The formula. This is the formula you need to know about Dirac delta function. If you do the Laplace transform, you simply get that e to the negative sc thing. Okay, so here is actual problem. Here's a little trick that you're going to see in the book is the following situation. Here's the autonomous system, left-hand side, all constant coefficient. And here is a nice and smooth external force. But you're adding this pulse in there. Usual smooth and nice forces added, plus a little pulse in there. And we have non-trivial initial condition. In that case, they're suggesting the following. Ignore the delta part. Just look at this equation, like that, with the initial value, and use non-Laplace transform method. It's absolutely unnecessary to go through that difficult process. Just use a usual method we learned before to solve this equation where delta is absent. But you got to take in all the initial value here. Yeah. So if you can solve this one using the Cramer's rule, all that, and solve this differential equation with this Laplace initial value. In that case, the Laplace transform, we're going to do this Laplace transform for the second part, and this here, y delta s is a simple, this as squared plus bs plus c. This one appeared exactly at the quadratic formula. If the initial value is 0, then we have k times e to the negative alpha s. Then we can do the inverse here, right? So Laplace transform is quick here because of this initial condition you put it in there. But put that initial condition to the other guy, which does not have any delta function or unit step function. So this one, we can use judicious guessing with, all that with earlier method we learned to solve that and add that. And they're claiming that this is going to be the solution. Because this left-hand side is the linear operator, if you do ty, it's going to be ty plus ty delta. That's the left-hand side. We saw that this is going to be the solution. Y hat here, I forgot. Y hat will give you f of t. This one will give you k times delta of t minus alpha. So this function satisfied this differential equation. It's called the principle of superposition. Now you have to check the initial condition, and here y equals 0. That picks up that y0 value. And this says it's 0 here, right? And y prime of 0 from this, the solution, picks up v0 here, and we put the initial condition must be 0. So this y satisfied this initial condition as well, because the other initial condition is 0 by superposition. So you solve this equation separately and put these two answers together, and it's going to be the full answer. And where you have to divide this initial value, all the initial value goes to the non-Laplace transform method. And initial value is going to be 0 for Laplace transform method, because this makes this Laplace transform easier. So this is what they have. It's an example. And I'll end it here. So order 2 linear equation on the left side. All right. This is nice function. There's no heavy side step function or anything. So for that one, which is what they're setting up in here, ignore delta and solve this full initial value there using guessing that, try e to the negative 2a 2t times a. And that a turns out to be negative 1 in here. And this is a fundamental set of this guy here. So you solve this one and it equals y hat. Now you have to solve the delta side. You copy exactly the same equation and solve this delta equation. So what is, I'm going to call this the y delta. What is y delta here? 2 times e to the negative s, right? Divided by this whole thing becomes equation s squared plus 6s plus 5. Yeah? And then inverse this one you practice. So you can get delta solution using the Laplace inverse transform of s. You see the unit step function kicks in? Yeah. Here it's going to be u of t minus 1 kicks in, right? Because of that factor. So this one here is a 2 times u of t minus 1 and Laplace transform all 1 over s squared plus 6s plus 5. And you do the partial fraction decomposition, all that. And then at the end, we have to do shifting. All right? That's Laplace transform involving unit step function. So that's y delta, and that's y hat. If you add them together, that's the full solution to this force model where this nice external force is there, and there's a sudden pulse added in there. Okay? So just remember, this delta thing is not a function. It's a shorthand notation of delta H. And later it's simplified to a simpler solution. So here it is. It's called Dirac, and it's called Dirac Delta. To me, is a non-function. Okay. All right. Thank you so much throughout the whole semester.